Okay, welcome everyone. We're happy to have Janna Levin, who's a professor of physics and astronomy at the Barnard College at Columbia University. She's a Guggenheim Fellow who specializes in cosmology, gravitational waves, and today she'll be telling us about black holes. She's the director of the science studios at Pioneer Works and does a lot of outreach and popularization of science. She's written several books, including How the Universe Got Its Spots, and of course is an accomplished novelist with the A Madman Dreams of Turing Machines, which won the Penn Bingham Prize. Her latest book is Black Hole Blues and Songs from Outer Space, and is the story of gravitational waves. Let's welcome Janna Levin.
Thank you. Thanks. It's a pleasure to be here. Thanks for having me. I'm illuminated. I feel like I'm glowing. I want to talk today about a pretty new project. I mean, we've been chipping away at this for a little while, but very new results about how to light up black holes. And we're talking about something that we're conjecturing might exist, which is a black hole pulsar, a very short and erratic short-lived and erratic pulsar built out of a black hole. And the elements we need for this are really just a magnetic field, some motion, and the black hole. And I'll describe to you how that emerges. It's always fun to begin at the beginning, so I thought we'd take a look at black holes in general. This is not a cartoon. This is a computer simulation by the physicist Andrew Hamilton, who's in Colorado, of what it would be like if we were to fall into a black hole that was between us and the rest of our galaxy. And we're seeing the gravitational lensing, the bending of the path of light due to the curved space-time as we fall into the black hole. And one of the things I love about this numerical experiment is how it reminds us that by now we're actually inside the black hole, by the way. We're inside the event horizon. And how it reminds us that black holes, while completely dark on the outside, can actually be bright on the inside. You have the light raining in from the galaxy behind you, and it comes focused at you like a blast of light. You would actually see kind of a bright white flash before you were crushed to death, right, in the singularity. And I'm quoting myself, but it's like a near-death experience, you know? You see the light at the end of the tunnel, only it's a total death experience. So the thing to think about with black holes is that they are nothing. There's nothing there, at least not on the surface, not at the event horizon. And so black holes earn their name of being completely dark. Of course, we see black holes indirectly because we see the havoc they wreak on their environments, destroying other stars, tearing down debris from accretion disks, twisting up magnetic fields, but we don't actually take pictures of black holes, at least not yet, maybe with Event Horizon Telescope on the horizon. But the point really being that black holes are dark. Now this is a computer simulation, very difficult numerical simulation, of what happens when two black holes collide. Those colored patches are not light. They're actually the painting of the curves in space, helpfully painted for us because we wouldn't see them otherwise. And what happens, as you all know, when two black holes collide is that they ring space-time like a drum. And like mallets on a drum, they create this ringing in the shape of the drum, which is a squeezing and stretching of space that we call the gravitational wave. And when the two black holes collide and finish colliding, they settle down to a quiescent black hole, a black hole that goes completely quiet. Now, even before the LIGO detection, we were anticipating these black holes to be completely dark, not dressed by other debris, not tearing down other stars, to be in complete darkness. So the gravitational wave detection, recording that ringing of space, is the only way, or was the only way that we were thinking of at the time, to detect bare black holes, right, without debris. And of course, when they collide, they're still dark because there's nothing there. There's nothing to collide. They're just regions of space-time. And when they merge, It's just empty regions of space-time. There's no material to explode, to crash together, to get bright, to get luminous. And the ring down and everything happens in purely gravitational wave form. So that was a prediction. That prediction took, was it 25, 30 years to solve even on a computer? It was such a challenging problem. And people really didn't anticipate how difficult it was going to be to do that even numerically. But now, of course, numerical relativists have gotten into their stride. They have incredibly powerful tools. They can throw black holes together and make predictions. This is what it would sound like. Could we maybe, is anybody here to cut the lights a little bit on the screens? No? Did we lose? I should have asked my AV person. Right here? Is it going to go completely dark? Full on. Lower down. Oh, that says full on. Oh, is that too dark? Okay. Okay. Because they're such pretty pictures. So here's what that would sound like. So when I say sound, of course, you all know that there's no sound in space. If you're a sci-fi fan and you hear people screaming when they come out of the capsule, you know, like it's a bad movie. If their hair's blowing, or something's hanging down. These are all bad things in space. So we know there's no actual sound in space, but the gravitational wave is closer to sound than just a vague analogy. It's literally like a ringing drum. I liken it, when I was in Professor Alexander's class this morning, I liken it to an electric guitar system. What LIGO is as an experiment, it's like building the body of an electric guitar. When you pluck an electric guitar string, you don't actually hear the sound until you plug it into a conventional amplifier through the body of the guitar. And in some sense, LIGO is like a giant musical instrument that's surrounding space-time, a region of space-time, and trying to measure the passing wave, the passing gravitational wave. And they play it through a conventional speaker system in the control room. You can sit there listening to the detector hum. So just to remind people, LIGO consists of 2 machines, one in Louisiana, one in Washington State. There's also an Italian machine, Virgo. Each one's 4 kilometers long, and they make an interferometer, where what you're really measuring is the location of the mirrors on the far, far ends of the long arms, the 4-kilometer long arms. And these mirrors are so delicately suspended that they're basically floating in space, at least in the transverse direction. And when a gravitational wave comes, they ring ever so slightly. And it is ever, ever so slight. It's less than 1/10,000th the width of a proton over the 4 kilometers. It's a spectacular measurement. So this is what it was predicted 2 black holes colliding would sound like. The famous chirp. Okay, so that would have been a long signal. This is another perspective on what the prediction looks like, where I'm actually showing the orbits. I like this one because you have a heavy black hole where their orbit is helpfully painted in yellow, and a lighter black hole orbiting around it, helpfully painted in red, and they're both spinning. And what's going on is you're seeing the entire plane of the orbit precess, and you can hear that when the plane is pointing away from you, or least optimal orientation, it gets quieter, and it gets louder in the most optimal orientation. And you'll eventually hear it chirp. So this is a highly eccentric orbit. We haven't seen anything like this yet. This would be real cool to see this. Okay. And it chirps. So those were the predictions. And then, of course, famously, despite the fact that they weren't quite ready for the detection, Ray Weiss said to me in August, right before the detection, it was 2015, right? I have my years mixed up, Rick, 2015 sound right? I think it was 2015. On August of 2015, Ray saying to me, if we don't detect black holes, this thing is a failure. It's been his entire life, his entire career devoted to this, and they're going into the science run, and he's nervous that it might not succeed, that the experiment's incredible, but maybe nature doesn't provide. So by now, the story is pretty well known that on the Sunday night, middle of Monday morning, the experimentalists felt they weren't ready to start the science run as planned. So they're delaying and they're interfering with their instrument, and they're doing things like slamming on the brakes of the truck along the access road, trying to create noise intentionally. Mercifully, they get tired and go home, Okay. So some of the experimentalists said the best thing I ever did for LIGO was get tired and go home. They leave it in observing mode, and within the span of an hour, a gravitational wave that was racing from 1.3 billion light years away finally sloshes over Louisiana. It's beautifully recorded, makes it across the continent, and is recorded in Washington. And this is a computer simulation, if it runs. Oh. Let's try this one again. This is a computer simulation of what was observed, which is two black holes, each about 30 times the mass of the sun, executing their final orbits together. You have to imagine that this could have been going on for billions of years, and they were further apart and getting closer and closer. And it's only the final, this has been drastically slowed down for us, 1/5 of a second that gets recorded, so 200 milliseconds. That gets recorded. And it rings down to form a perfect black hole. Of course, we couldn't see this because it's so far away. We couldn't come anywhere near imagining to measure the shadow, but this is what they heard. And you hear, it's the perfect chirp. Now, the other details of the spins and the orientations is really hard to hear in this signal because it wasn't loud enough until the final 1/5 of a second. And even so, more power came out of that collision than any other event that has ever been detected in human history since the Big Bang, right? And none of it comes out as light, completely dark. Now, this detection of the two neutron stars was the most recent excitement that came out of LIGO, because neutron stars, when they crash together, and this is a cartoon, you can hear it sound similar, but neutron stars are made of real stuff. When they crash together, they actually physically crash together, and so it was followed by fireworks. And the fireworks have been watched for the past year, and it was spectacular. Every waveband got a chance where there were different epochs. And I'm not an expert in gamma ray bursts, but this was really one of the most widely studied astronomical events in history already in a year. So the excitement is that LIGO, when it starts to hear something, triggers all of these other instruments and satellites to swing over in the rough direction where they're anticipating the source to be, and allowing for this multi-messenger astronomy, this very complex portrait, both in pictures and in sounds, of what is going on in the system. And yet black holes are going to be excluded from that multi-messenger portrait, most likely. We'll only be able to detect them completely dark. But this leads to what I've become interested in lately, which is a black hole neutron star system. Now, you might think, oh, well, black hole neutron star systems are going to be bright because the neutron star is made of stuff, right? And black holes tear stuff apart, so it's probably going to destroy the neutron star, and then that would be luminous. But it's actually not the case. Most black holes, even if they're only a few solar masses, are too big to tidally disrupt the neutron star. They'll swallow it whole, like a marble falling in, right? And the reason for that is, if you think about it, if you stand on a basketball, the smaller it is, the curved object, the more you notice it's curved. If you stand on the Earth, you don't notice it so much. So the tidal forces, which have to do with the different forces on the sides of the neutron star, are actually much weaker the bigger the black hole, okay? So most neutron stars will fall in unaffected, and so you would fear that this whole system could go all the way through to the end and remain dark. And that's why we started thinking about other ways to light up the black hole. And our first stop was to ask, look, black holes are kind of like conductors in a weird way. They swing things around dramatically, and neutron stars are giant magnets. And when you swing around a magnet, you can make a battery. So we started to call this the black hole battery. And the idea is that if it's just Faraday's law, essentially, but in a highly relativistic setting. So you take a magnet. If I could do this, presumably with a strong enough magnet, although I've never tried. If you unscrew a light bulb and you hold it in your hand and you wave a magnet around, just by Faraday's law, you create electric fields and you can drive currents and turn the light bulb on. So we're arguing, well, a neutron star is basically a giant magnet. And if the neutron star is waving around the black hole, it's going to create an electronic circuit. It's going to create electric fields. And what we have to do then, the task is to estimate how much power is in that battery. And so we're not even that close to describing all the channels for lighting it up. That would be like figuring out what the light bulb is, but we're just trying to say how much power does this battery have. So we draw it like a little circuit. We have, the horizon of the black hole it's really a unipolar inductor, but that sounds nowhere near as good as black hole battery. So I called it a black hole battery. So we kind of pretend the battery is localized on the horizon. The magnetic field lines would provide the wires along which current can run. The magnetosphere of the neutron star provides electrons and positrons, so it provides conducting particles to run along the wires. And there's some resistance in the neutron star. It might be superconducting, it might be very low, and there's some resistance in the magnetosphere. So we have this nice little kind of circuit diagram thinking. And the calculation we do is much more gruesome. We boost into weird frames. We have a complete magnetic dipole. We put it on arbitrary world lines. We can really find out what the electromagnetic fields look like in some pretty good detail in the limit of a big black hole. But I'm just going to sketch out the kind of essential Faraday's law elements, which is that you have some velocity through a magnetic field, which creates an electric field. Then you just calculate the EMF, the potential drop, right, across essentially the event horizon. And from that, it doesn't matter what the details are, but we know it depends largely on the magnetic field of the neutron star. We have some relativistic terms in there, and it depends also on the spins of the objects. You get more juice out of it if they spin. And so this accelerates charges, and we simply compute the power. What's the power in this setup? And without knowing, we know the resistance of the black hole, actually. It's one of those properties you can calculate that's fundamental to a black hole event horizon, what its resistance is. And it scales like the magnetic field squared, the mass of the black hole inverse 4, actually. So the bigger the black hole, the weaker the power. And of course, the velocity and the velocity squared. So the faster you're going, the more power you're going to get. So at the final stages, when they're going 0.7 the speed of light or more, is when you're expecting to get the greatest power. Also, the magnetic field is largest the closest they are together, because dipole fields drop off like 1 over r cubed. So the further away they are, the weaker the phenomenon. So just to give you a sense of this, I should say that if I take a neutron star with a dipole on it, so it's got this huge magnetic field, 1 trillion times that of the Earth or more, 10 to the 16 Gauss, and it's spinning, there's actually a point, because of the spin, where the field lines can't stay connected. They would be traveling essentially faster than the speed of light. So what happens is the field lines kind of open up. And so to make this circuit, you have to be within the light cylinder, it's called, of the neutron star. You have to be within the region where the magnetic field lines are closed. And that we just calculated for a 10 solar mass black hole and a neutron star spinning once a second, that's about 1,000 Schwarzschild radii. So it has to be in pretty close. 1,000 Schwarzschild radii is actually quite close. In units of the gravitational wave timescale, it would take about 20 years from that point to get to complete merger. So it doesn't even connect until that point, and then you start to get a weak battery. Oh, yeah, we sort of turned them down, but that's okay.
That's fine.
No, I think that's good. Is that good? Yeah, okay. So then it reaches a maximum as you actually hit merger, where we expect to get significant power. And the power we estimate is around, 10 to the 50 is very, very big, 10 to the 50 ergs per second, but that's an overestimate, really, because we cranked the magnetic field up of the neutron star to the maximum value we've ever seen in the universe. And so it's very high. This would go down by quite a lot if the field went down to 10 to the 12 Gauss. It goes down by 10 to the 6. So, 10 to the 12? No, 10 to the 8 goes down. So you're then more in the 10 to the 42 ergs per second. But here's the thinking. The thinking is you start this electronic circuit. If it was in our galaxy, maybe we would see it, but that seems unlikely. If we're at extragalactic distances, we're waiting to the final millisecond or so for this flash of electronic power to become available. And then we're just guessing. after that. So we can do these calculations beautifully on paper, but exactly how that power gets dumped into a light fixture, we don't know. We could expect jets are very common. We could expect something like a weird composite pulsar. We might expect a fireball. There's definitely synchrocurvature radiation. It might be multi-band. So it's very hard to predict what it would look like, but our prediction is really in the numbers. It's really in the comparison of the numbers. That this much power, short-lived, turns on, turns off. It's not a gamma ray burst, because that's not what gamma ray bursts look like. We can look at gamma ray bursts now for a year and see stuff coming out of it. This would be a much more brief phenomenon. So with all the transient surveys going on, we might be able to have a detection that from gravitational waves we know is black hole neutron star, and then in the luminosities we look for these kind of bright flashes. It could even be something that looks a lot like a fast radio burst. Okay, so this is our challenge. This is where we are. We don't know how to do that, but we're close. I've already said this, that these are the channels in which we might expect some luminosity. So we're going to hold out. So what's the takeaway about the black hole battery? The black hole takeaway is that we expect a bright transient in the final millisecond. The fact that this happens physically is not disputed. What you could worry about is whether the magnetic fields stay that large for that long. How many of these are there out there? Will the luminosity be sufficient? But it's definitely a phenomenon that should happen. The time scale is pretty well set by gravitational radiation losses, so we know that number well, and that helps us break degeneracies. And the maximum power will tell us something about the magnetic fields of the neutron stars. We could use it in the negative, although that's never so exciting. If we see black hole neutron star collisions and we don't see anything, then we know that the magnetic field is small. So we can use it in the inverse way. And as I said, I don't make very rigid claims about predictions of what it would actually look like, at least not yet. Now, once we got to this point of being very convinced that this is just going to happen, you're going to form this black hole battery, we started to think about charge on the black hole. Now, it seems silly to think about charge. I mean, I know when I was in graduate school, everyone told me, forget about it, it's not interesting because there's so much ambient charge in the interstellar medium that as soon as you put any kind of charge on the black hole, it's just instantly going to discharge. I mean, it's not going to be able to maintain its charge. That argument is flawed. It only took me 15 years to think about it. It's hard enough to realize that that argument is flawed. And the reason it's flawed is because when you have a black hole, for instance, in an external magnetic field, the lowest energy state is to acquire charge. And it's not obvious. It's not obvious that that's the case. But what happens effectively is you don't have to worry about the exact calculation. I just flash it up there because it's pretty. This is one of my pretty pictures. Wald actually, it turns out, had done this in 1974, and I don't know why so many people forgot about it. It's an absolutely stunning paper that I had to rediscover because I don't do literature searches properly before I do my calculations. So I discovered Wald had already done this, but he did it so elegantly. What Wald realized is that you can solve Maxwell's equations exactly for a black hole in an external magnetic field by leaning on the symmetries of the space, that you could show that the vectors which describe the symmetries, known as the killing vectors, that those vectors were electric potentials. And that was really a stunning little proof. It's very short. And you go through the whole thing, and what you find is that while far away from the black hole, you have a magnetic field that's uniform. Where the black hole spins, near the black hole, you twist up the field lines, you actually alter the electromagnetic properties, and you create an electric field. Again, it's not that different from a Faraday's law type argument. The spinning black hole creates an electric field. Now, once you have an electric field, it's like charges want to screen electric fields. That's what they do. In the presence of electric fields, charges move. And in conductors, you all know that they move until they can kill the electric field inside the conductor. So what this situation would have the feature, it would have the feature that it's pulling and drawing charges from the magnetosphere of the neutron star along the field lines, and the magnetic field of the neutron star is providing the external field, and the tendency would be for charge to accumulate. So you can calculate exactly what that charge is, and again, we do it more relativistically, but the value that Wald found, which is the maximum value of the charge, is twice the magnetic field of the external magnetic field times the spin of the black hole. So when the black hole stops spinning, it discharges, and if the magnetic field it's immersed in is weak, it's not very significant. But when you're looking at these huge values of the magnetic fields for large spinning black holes, you acquire a significant amount of charge on the black hole. So here we have a kind of similar argument, which is that when the black hole enters the light cylinder of the neutron star, and now it's immersed, it's not a perfectly uniform magnetic field, obviously, but the phenomena is going to be the same. We can calculate what the maximum charge is on the black hole. And we find in units of the mass, which is how we quote everything. I can give it to you in coulombs, but I don't really know that that's useful. It's about, for a rapidly spinning black hole, 10 times the mass of the sun, and a magnetic field of 10 to the 12 Gauss, let's say, the charge is 10 to the minus 7 m. And what that tells us is that we can use the space-time metric of a spinning black hole without worrying about adding charge as part of the deformation of the space-time, because it's still small compared to maximum. And so as it enters the light cylinder, which is about 10 to the 3 Schwarzschild radii, the charge is 1 billion times smaller than maximal. And then as it approaches, because of the 1 over r cubed behavior of the magnetic field, it slowly rises. So as you approach the horizon, the charge spikes, and you end up with a significant charge on the black hole. Even though the charge is significant, so 10 to the 33 times the electron charge, it still amounts to very little mass. So you also don't change the mass of the black hole that much. It's like throwing in 1,000 kilograms so worth of electrons or positrons. So you're not actually changing the mass very much. It turns out also, I should say, that the spin of the black hole, when it's aligned with the magnetic field, the charge is positive. And when it's anti-aligned, the charge is negative. It acquires a negative charge. So maybe...
Charge falls right through the event horizon.
Right through the event horizon, yeah. So, yes, and so the interesting question is that stable, or will it continue to flux? And so what we were able to show was that even though it hits this maximum charge, it doesn't just go quiescent, because the field lines are so complicated around it that it continues to put charges on stable orbits, but orbits. So you have positive and negative charges in this fluxing area around it, which can be radiating. So these charges would be constantly radiating as they're flowing around without changing. And so again, this is, we don't really know how to predict where the signal is or when it's going to be there. But because we have charge, because it charges up, we expect that to be visible, and then we expect the fluxing of these charged particles in the magnetic field to be visible as long as it's going on as a process. So let me connect this to the Nohair theorem, because that's not the only thing that happens. It's not just that it charges up and you see fluxing charges. The whole game for lighting up compact objects is to accelerate charges, to make a particle accelerator out of the system. And that's what we're doing here. We're making a particle accelerator out of the system, and then we want to see things. We want to see it light up. But there's another phenomenon that happens that I actually really love, and it seems counter to the Nohair theorem. So people often say, and again, I was told this all the time as a graduate student, black holes have no hair, so they have no magnetic fields. They cannot, in vacuum, support a magnetic field. That's actually not the Nohair theorem, actually. The Nohair theorem says that, that the only magnetic field a black hole can support is consistent with a monopole of charge, because we know black holes can have charge, right? The 3 quantum numbers that a black hole can have are mass, spin, and charge. And if you like magnetic monopoles, you can add magnetic charge. But when I have a charged sphere, and that charged sphere spins, I actually create a magnetic field. That creates a magnetic dipole. So a spinning charge if I have a black hole with charge on it and it spins, then I do create, in fact, a magnetic dipole on the black hole in vacuum. Now, it requires this external field to charge it up, but even if I imagine taking that field away and taking away any other sources of charge so that it can't discharge, I will have a little magnetic dipole. And that becomes super interesting, because then you're saying the black hole is its own pulsar, right? Not just that it's moving through the magnetic fields of a neutron star, which may or may not be a pulsar, but that it has all of the natural ingredients to become its own pulsar. It has its own magnetic field. It can start to create its own magnetosphere. So the magnetosphere is self-generated by a neutron star. We think similarly, when the electric fields and the magnetic fields get large enough, that it will begin to create its own magnetosphere as well. And then you really have all the ingredients of a pulsar, which is a spinning, strong magnetic field that is capable of accelerating particles. Now, even traditional pulsars are not well understood, even despite all of the 40, 50 years of observations. It's still hard to understand what the mechanism is at play. So I'm not going to pretend I know what the mechanism is at play, just that I know that I have the fundamental ingredients to create a black hole pulsar. Now, the ways in which it would be different, for one, we're going to be seeing strong relativistic effects when this happens. And just as I showed you the orbits of the two black holes, where you saw the red and yellow lines, this entire system is going to be precessing. So now the spins of both objects are precessing around due to relativistic precession, the lens-thirring effect, and frame dragging, right? So this is a well-known relativistic effect, but it's going to be happening at its strongest in these final phases, and the entire orbital plane is going to be precessing as a result of this. And so it's not going to look like a pulsar in the traditional way that we search for it, which is for a perfect clock. And so we can't search, it's going to be an erratic pulsar, if anything. But I still think it's a pretty spectacular prediction. And then what do we have? Then we're at the final stages of the lifetime together. One thing I should actually qualify as well is that when you create this magnetosphere, you're no longer in vacuum. Now, a lot of people start to talk about force-free magnetospheres, and things can change a lot. So we were worried that maybe that instantly neutralizes the black hole charge, that a black hole in a force-free environment would no longer acquire the charge. But then we looked closely at some of the most famous solutions, like the Blandford-Znaiec solution for a black hole in a split dipole situation. And we actually went back and calculated Gauss's law, which I don't know if anyone had tried it before. And we can prove that, in fact, it retains charge even in these famous force-free models. So it doesn't appear like that would negate any of these effects. I'm really confused about the time, so I'm going to leave a lot of time for questions. Is that all right? Because my thing says something different too. Okay, so now what happens? Now it absorbs the neutron star, and it takes away the external field, but now it has its own magnetosphere, and that means that it can keep that magnetic field for a little while. How long, we don't really know. But we expect there to be a pretty clear, which is what we're working on now, post-merger signal of the black hole absorbing the neutron star, taking its magnetic field, and staying around for a little while. And again, the real interesting distinction between a black hole neutron star lighting up, besides it's going to be kind of vapor thin and fast, is that you won't see this incredible legacy of these fireworks afterwards. You'll see something that is not really natural gamma ray timescales, maybe shorter, and so will look distinct. So before I open it to questions, what's the takeaway from this? Black holes in magnetic fields do acquire charge. If the magnetic field is large enough, it doesn't matter how much charge is available to it, it will be a charged object. It's the low energy state. And you can think of it in the most simple conventional terms. You've created an electric field, charges simply will be accelerated until that electric field, if doesn't vanish, at least until none of the field lines continue to reconnect with the event horizon. So the electric field doesn't vanish, it stays around, but it just doesn't pierce the event horizon, it doesn't bring any more charges in or out. What it does do is it accelerates charges around the black hole, so we expect it to stay bright. So the charged fluxes are a really interesting question. There's also a lot of chaotic dynamics around the black hole when the particles are charged, which is pretty interesting. So we really believe that a black hole, both through the black hole battery and through the charging phase, is going to power hopefully bright transient. I can't swear it's going to be bright. I said bright to be optimistic. But of course, we live under the possibility that it'll be a terribly faint transient and we won't catch it, which would be disappointing. But it is, as far as I know, the only multi-messenger counterpart to a black hole neutron star merger. And so that makes it something that we should try to be optimistic about. The maximum power is definitely set by the neutron star magnetic field. So if those fields don't get boosted back up, or if they decay over the lifetime so that they're too weak, then that would also push it outside of visibility for us. And then finally, that the charged black hole has its own magnetic field, and thereby all of the features for an unstable and transitory pulsar. Thank you. I talked at a real New York clip today. That was like, whew. Yes, did you have a question? Please.
So I'm interested in the observational signature before the neutron star falls into the black hole. I'm thinking that the place you will find this is by pre-matching something in the neutron stars, in the precession of the axis or something, because it'll behave completely different from a standard binary pulsar.
Yes, exactly. And I think that's why I don't even know how to look for. I mean, you look for pulsars by hoping it doesn't have features that are unstable or transitory. That's exactly the opposite of what you look for. So it could be, though, that these deep sky surveys, these transient surveys that are just looking at everything all the time, are going to see something, and they might. I was talking to somebody close to one of the groups recently, and they're saying they should probably throw that away, right? So we might have even seen something that we didn't hear in gravitational waves, but we're throwing it away because we don't know that that could be exactly what we're looking for. So I think I need a collaborator with more of a data analysis leaning. Hint. I wanted to start a dating app for researchers where it's like, black hole theorist seeks the same. Must live on the East Coast. Yes. Oh, was that the end of your question? Yeah.
Great talk. I have no intuition for this because it's relativistic. So if this, once a dipole is set up, let's say, in this pulsar, the black hole pulsar, and let's imagine it radiates electromagnetically, let's say. I don't know if it does, but if it does.
Yeah, so then it would.
Do you expect the polarization to be different? Yeah.
It's so hard.
Radiation?
Yeah. Who knows more about the radio pulsars? They're polarized, right? You see the light is polarized because it's very coherent. One of the things you don't understand is why this high energy power is reprocessed into this lower energy range of the radio frequency. And there's very complicated theories about bunching of electrons creating coherent behavior. If something like that were to work in this context, we could get radio with polarization, and that would be fantastic because you can see radio waves from further away than gamma rays, right? So gamma rays, you need huge energies, 10 to the 52, you need these really huge energies. And if we're down at 10 to the 45 or 6 ergs per second, then we'll be better off if it's coming out as coherent, polarized radiation in the radio. That would be spectacular. Fast radio bursts, for instance, are seen at extragalactic distances, presumably. So whereas gamma rays, are hard. They're harder to detect. So, yeah, all of that is in whether it has time to have that kind of coherent process happen before it turns off. I mean, I think that's going to be that's going to be a numerical, something that has to be done numerically.
So
Yes.
I'm wondering if after the merger, the black hole retains its magnetic moment, which was external, but stays external according to what you told us. Wouldn't you get in the trouble with information paradox? Because I could imagine that I throw a single electron in a black hole, I immediately measure the change in magnetic moment and magnetic dipole, and I basically know what happened inside the horizon.
Okay, so let me see. So we can definitely take a charged black hole in an imaginary universe where that's the only thing in the universe and spin it, and it will have a permanent dipole moment because there's nothing to discharge it, right? It's energetically less favorable to be charged once I take away the external field. So if charges were around, it would want to discharge. But that should be a totally
That's a
viable.
stationary solution.
Right, so now you're saying, okay, that's totally real. There's a black hole in a universe by itself, it's charged, it's got its own magnetic dipole moment, lives forever, and I bring in one electron, and I'm just rephrasing your question so I can think about it. So the electron falls in, and you're saying, does that violate the information paradox because I can measure the change in the magnetic dipole moment and
Yeah, in a sense, I don't see the electron falling in, but I could infer that one electron fell in just by measuring the magnetic moment.
I would say that is not a problem because you could always have electric hair. You could always have electric charge. And so the Nohair theorem isn't going to counter that argument. In other words, let me rephrase it. If I'm a co-rotating observer who doesn't see the black hole spin at all I see is electric field. So all I know is that the charge of the black hole has changed. And that should be totally kosher. I should be able to say, oh, I know the charge, spin, and mass outside. So it's the other information that I lose. It's all the other quantum numbers that I can't recover. But charge is the one thing I can know from the outside. Does that make sense? More questions? Oh, over here, we got David.
So the outside of a neutron star has the same solution to Einstein's equations as a spinning black hole. So I guess I'm wondering if your calculation could give some insight into how the fields around a neutron star are formed, turning it into a pulsar. It's such an interesting question. I did go back to look at the pulsar description, and as you said, it's just a black hole that hasn't made it far enough. It's the Kerr solution of the space-time. But the difference is, since it doesn't have a Nohair theorem, it has an intrinsic dipole, and so it is able to just sustain itself. But it is also charged. The neutron star has charge, and again, you just do Gauss's law, assuming a force-free magnetosphere, and you're going to have an electric field that's V cross B, and that's going to tell you that there has to be charge on it by Gauss's law. So the neutron stars are charged, the pulsars, but the big difference is because of their gooiness, and you can see it from the outside, and they're these wild superconductors, their own magnetic fields are very complicated and are very powerful. So the charge on it is small, and so the dipole generated by the spinning charge is small. It's totally dominated by this other magnetic effect. So I think a lot of the mystery of neutron stars, I think it's twofold. One is, what is the equation of state, and what is the nature of the superconducting matter? That's a big mystery, so we don't understand the magnetic fields. And the other is that we don't understand where these gaps are that allow for acceleration, because if it's force-free, there should be no forces. There should be no acceleration of charges outside, and so somehow there are these regions where the charges are making it, breaking the force-free rule, and they're becoming accelerators. And that seems to be a very hard problem. There's a question up here.
So suppose that the black hole is surrounded by something like axions, for example, because of superradiance, let's say. Mm-hmm. And then when the strong B field crosses that, it will probably generate a bunch of photons. And can you tell us a bit more about that bright transient, and if it's possible to tell for example, anything exotic out of the bright transient you're expecting?
Yeah, you mean so other physics that we can't yet detect elsewhere, things like axions. Is that what you mean? Right. Yeah. I've thought about it a little bit. I'm not sure. In some sense, because the space-time seems to still be the Kerr metric, it's not that different. It's not as though the dynamics changes between the black holes. I'm not really sure what I would look for, but I can't say no. I can't say no. I don't know yet. I mean, if the magnetic fields are strong enough and they're around the black hole, you would kind of say, well, why would that physics be any different than the pulsar physics? Why wouldn't pulsars have already told you something about axions and that why the black hole? I mean, to David's point, they're practically black holes, you know. So I guess I'm just not sure. And there's another question here, I think.
Just a naive question. How about the supermassive black hole at the center of our own galaxy? Would you see neutron stars falling into it?
Yeah, I asked exactly the same question. So as soon as this paper was finally out, I called Shep Doleman, who's on EHT, the PI for the Event Horizon Telescope, and started bugging him about it. And then when the paper went on the archive, you know how you get all those other papers saying you didn't cite me? So I got, you know, a wave of those, and among them, somebody had looked at this. Okay. Somebody had asked, not about neutron stars in specific, but they had said estimating what the median magnetic field is in the center of the galaxy, how much charge could you tolerate on the supermassive black hole? All they can do is bound it. So right now they just have a bound on it. But yes, it could be interesting for the Sag star as well. And I've been trying to think of any ways to make magnetic fields. And as we were talking about today, you know, you with a lot of people who I've met with today, it's hard to make big magnetic fields. And so, but anywhere you can make magnetic fields and put black holes in them, this is going to be something interesting to think about. So if you can think of a way to make magnetic fields outside of neutron stars that are large, I'm all ears. There was one other scenario. It could be that black hole systems do this as well, but that's just much less likely because it's hard to think of how they got charged up in the first place. But it's not inconceivable if you had two charged black holes that they would light up as well. But presumably, it's hard to keep the charge on those because there's no external magnetic field. Yes?
Yeah, why a neutron star is a magnetic dipole? Can that be a magnetic quadrupole to reduce the external field completely?
Yeah, I think it can be some pretty crazy things. So you're saying to remove the external field completely? Yeah, it could be. But we're not even probing the details of the dipole, let alone higher multiples. We're just pretending it's a uniform field for now. You know, we're just doing the easiest step first. When we do the full black hole battery calculation, we actually put in a full dipole on a completely arbitrary world line, and we can do the whole calculation. But the Wald argument of the charge is actually very hard to calculate if you're not in this kind of uniform system. So I mean, from what I understand about neutron stars, they can get quite complicated. So I wouldn't yet conjecture if the field is more complicated than a dipole. But what would really matter is its fall off, how quickly it falls off with distance from the neutron star. Because that's what makes it very weak when you're only a few hundred Schwarzschild radii away. That still suppresses the magnetic field the black hole's feeling by quite a lot. So I guess the only thing that would be super relevant for us would be the fall off rate, if that was more gradual. Yes?
Can't resist making a quick comment. So the neutron stars they have complicated magnetic fields, but there's no easy way to get rid of the dipole component. So they can also have quadrupole components, but because the stars from which they're made are spinning objects which naturally produce dipoles via the dynamo process, you end up.
Oh, I'm sorry, you were
generating a
saying
dipole field.
only the higher multiples and not the dipole. Is that what you meant? Yeah. Yeah, I see. Yeah, right. So they all have dipoles, yeah. One more.
Hi, I'm a solid state physicist. I'm really intrigued by the idea that the black hole horizon has a resistance.
Yeah.
I kind of want to know what it is.
It's actually the resistivity of free space. It's actually just that exact value. What is that? 2 pi over something ohms, I don't remember exactly, but you calculate it by pretending the black hole has a membrane on it, and you treat it as though it was a hypothetical conductor with all the same properties. And by doing that, the membrane paradigm tells you you can actually calculate properties, intrinsic properties of the event horizon in this way. It is exactly like a conductor, but it has a resistivity of free space. And it has something to do, I used to know the answer to this better, but you know, the resistivity of free space has something to do with the way waves propagate in empty space. So it has something to do with the way the waves propagate at the event horizon, that it has that intrinsic property. So it's like saying the laws of black hole thermodynamics, you know, the temperature of the black hole, the laws of black hole thermodynamics. Like we know black holes have a temperature inverse 1 on m. We know that the entropy goes like the area. And so similarly, we can do that with its electromagnetic properties. Yeah. Okay, is there a last question? You guys had had me talking since 8:30. I just want you to know that. I don't mind being done. Thank you.